Thanks, Bishan, and thanks to the organizers for having me here. It's good to be back again. Thanks, Mauro. Okay, yeah, this is a work in progress with Marzieh Forough from Prague. And so let us begin by recalling the definition of our completely positive map. So we have two C-star algebras A and B. A linear map phi is called completely positive if for all n you take the amplification. So phi n is called the amplification. So you take a matrix, n by n matrix with entries in A, apply phi entry-wise, and then this is how phi n is defined. So phi is called completely positive if the amplification is positive for all n. So which means it sends positive matrices to positive matrices. So yeah, a star homomorphism has to be CP. So that's the one. This is a bit more convoluted, but yeah. So define phi from a C-star algebra A to the set of bounded linear operators on a Hilbert space H by the formula where, so you take a representation first, phi of A on K. K is another Hilbert space. And you take a bounded operator from H to K and you compress the representation. That's what phi is. It turns out that phi is CP. And as a special case, when the domain is the matrices over C, a map from the matrices onto a C-star algebra is CP, if and only if you evaluate the map on the canonical matrix units, you get a matrix with entries in A. That matrix has to be positive. So this is an if and only if. Right. So J will be fixed throughout the talk. It's a closed two-sided ideal in a C-star algebra B. Qj is the projection. A completely positive and contractive map phi from A to B mod J is called liftable if there is a CPC map which is completely positive and contractive psi from A to B. Says that when you go down, you get phi. The question is, we will be interested in a variation of this question. The question is, when a CPC map liftable? Yeah. So let's begin with some remarks. So you have a C-star algebra C, have a closed two-sided ideal I. It turns out it's an easy exercise that any positive element in the quotient leads to a positive element upwards in C. Right. So since a CPC map from MNC to B is given by a positive element in the matrix ring over B, a CPC map from MNC to the quotient leads to a, well, it's not CPC, it's just CP because you get a positive element. But there is a trick which says, if there is a CP lift, there is also a CPC lift. So you can do stuff to the CP lift and get a CPC lift. So yeah. So let me draw a diagram. So it's B mod C, here is MNC. So we want to lift this to this. And so suppose this map factors to this. We know that maps from MNC lifts, so it gets to here. And when you compose the lift, you get a lift. So that's gives what is called a nuclear map. So it's, yeah, so CPC map theta from A to B is called nuclear if it's in the closure of such maps in a suitable topology, which more precisely is if there is a net of CPC maps that factors through, so phi lambda from A to some matrix ring and phi lambda from that matrix ring to B, such that this happens, this limit goes to 0. This is called the point norm topology. And the C-star algebra A is called nuclear if the identity map is nuclear. The first example should be commutative C-star algebras, and to repeat a joke, partitions of unity were invented to prove that the commutative C-star algebras are nuclear. F algebras are nuclear, whatever they are. And interestingly, all amenable discrete groups, the group C-star algebra is nuclear, and it's a if and only. And this is a fundamental theorem by Choi and Effros, which says every nuclear CPC map from a separable C-star algebra A to a quotient is liftable. So in particular, if you take A to be nuclear, separable, then any CPC map to the quotient is liftable. So this is one of the fundamental results, and it's way old. Yeah, so we'll be talking about continuous fields of maps. So let us first define what a continuous field of C-star algebra is. So X is a locally compact Hausdorff space. A C0X algebra is a pair A theta, where A is a C-star algebra and theta is a star homomorphism from C0X to the multipliers of A. So that. So this is called non-degeneracy, which means so if A were unital and X were compact, then this first condition would be theta is unital. And the second thing is C0X. So the map theta gives A C0X module structure. The second condition says that it acts centrally. So yeah, Mx is the maximal ideal corresponding to X. Fix a C0X algebra. So we would like to get what call the fibers. For that, we define the closed linear span to be, so Mxa is the closed linear span of all the products. It turns out to be a closed two-sided ideal. And the quotient of A by this ideal is called the fiber of A at X. It's denoted by AX. We write AX for like, so A is in A, the image of A in the quotient is written as AX. So the map for a fixed A, X going to norm of AX is upper semi-continuous. And it turns out that you can recover the norm of the original A by taking the supremum. So it's exactly like what for functions. And if this map is continuous, A is called the continuous field of C-star algebras. Right. So the morphism that are allowed between two C0X algebras is a C0X linear map which intertwines the module structure. So more precisely, this is the formula. And such a C0X linear phi gives you fiber-wise maps for all X, phi X from X to Bx. And we need so what is called a pullback. So Y is another space, and you have a map from Y to X. A is a C0X algebra. The pullback F star A is a C0Y algebra such that the fibers are given by, so the fibers of the pullback at Y is the fiber of A at F of Y. Right. So now we're going to so everyone knows what a groupoid is. It's a small category where each arrow is invertible. So this is just a notation. G0 is the set of objects. G2 is the composable arrows. S is the source map. R is the range map. A topological groupoid is a groupoid with a topology such that everything is continuous. Example, of course, G for a group is a groupoid. A bit difficult is the following. So take a group and make it act on a topological space X from the right. Then we get the cross product groupoid, which consists of triples Y, G, X. So it's X you start with, G is the one that's acting, and Y is the thing that you get after the action XG. The source is obvious X, the range is again obvious is Y, the composition is the obvious one, and the inversion is also like flip everything. So what we want to define now is how a groupoid acts on a C-star algebra. So start with a locally compact Hausdorff groupoid, and A is a C0, G0 algebra. So G0 is the base of G. Yeah, so a G action on A would be a family of isomorphisms. So where if G were a group, then alpha G's would be an isomorphism from A to A. But since where G is a groupoid, it should be from, so A, the fiber of A at source of G, to the fiber of A at range of G, such that it has the action condition. So a continuous action would be with some sort of continuity on this family, alpha G's. More precisely, a G algebra is a pair A alpha where A is a C0, G0 algebra, and alpha is a star isomorphism. Importantly, it's C0 G linear, so that we can go fiber-wise from the pullback of A to G via the source to the pullback of A via the range. So we have for each G, alpha G's from like what we want, which has the action property for all GH, all composable pairs. Of course, G is a group, A is a G algebra. So in this case, the pullback of A is A times C0G, and similarly, the range R star A is A times C0G. then G viewed as a groupoid, the action alpha can be translated into this. So it takes a function. So I identify A times C0G as A valued functions on G that vanishes at infinity, and then alpha is to evaluate F at G and then apply alpha. Furthermore, if X is a G space and A theta is a C0X algebra such that theta is G-equivariant, which in Kasparov's notation is a G0X algebra, then A becomes naturally the G algebra, where G is now the groupoid X times G, the cross product groupoid. And these algebras appear naturally. For example, if G were a sigma compact group, H is a closed subgroup of G, and A is a H algebra, then you can, so there's this induced algebra, which now is a G algebra, but it turns out it's also a G. The space is the set of right cosets. So it's a G C0 H over G algebra. Yeah, so the problem is that we are interested in now, the A alpha and B beta are G algebras. J is a J-invariant ideal in B, which means like take the fibers of J on the source of G, you apply the action, you get the other fiber at the range. And phi is a C0 G0 linear CPC map onto the into the quotient. That's how this diagram commutes. So this is the equivariance property for the action. So on the top horizontal arrow, the alpha G is the action. Below it's beta G, the action on the quotient. So I write beta G again. And the vertical phi's are the fibers of the map I started with. What we want is a C0 G0 linear lift to the upward. So it's B, says that it's again equivariant for in this sense. So let's see what this means when G is a group. So again, we are in the same situation. So now this is the equivariance is this diagram, which is pretty clear. So it's just phi is equivariant with respect to the corresponding action. And what we want is again a lift, such that this diagram comes, which is again equivariance of psi. One more special case, we take C0X algebras A and B. J is again G-invariant ideal, phi is a map, C0X linear. Now it turns out, so the G action takes the fiber at X to the fiber at Gx. So this is the diagram that we get for equivariance of phi. What we want is a C0X linear lift psi, so that this diagram again comes. So it's the same diagram, but the fibers are, so since the action does not take the fiber at X to itself, it takes the fiber at X to Gx. Yeah, so now we have some remarks. So to have an equivariant lift, it's necessary to have a lift. So an equivariant lift is a lift. So it's a necessary condition. What we'll see that this is also sufficient in a suitable sense. So what we'll do is we'll use a subtle averaging technique from Kasparov, and in the groupoid setting, it's legal. So the equivariant KK theory, and we'll average the ordinary lift to get an equivariant lift, but it's not just integration with respect to something, it's much more subtle. For that, we need to know when a C0 G0 linear CPC map admits a C0 G0 linear lift. Otherwise, we cannot average. Of course, one guesses that the class should include what's called C0 G0 nuclear maps. The definition of a C0 G0 nuclear map is same, except for the building blocks you have M and C, you tensor it with the C0 G0 and demand that so all those maps are C0 G0 linear. And again, similarly, a C algebra is C0 G0 linear if the identity map is it's nuclear, C0 G0 nuclear. So a striking theorem by Boffel says, so X is my G0 here. A C0X algebra is C0X nuclear if each of the fibers is nuclear and the whole thing is continuous. That means that function X going to norm of AX is continuous for all A. So in order to have C0x nuclearity, you need to have all the fibers nuclear, and it has to be continuous, otherwise it won't be. So we see, suppose I have a C0x linear map from A to the quotient and go to the fibers, phi x from AX to the corresponding quotient. For a C0x nuclear A by Bogel's theorem, each of the fiber is nuclear. So I get by Choi Effros, this phi x is liftable. So I get some lift. The problem is I may not be able to glue them together to get a C0x linear lift. This is what a theorem by Kasparov and Scandalis say. So let A be a separable C0x algebra and phi a map from A onto into the quotient, which is C0x nuclear and CPC. Then phi is liftable. And so phi is liftable in the sense you get a C0x linear lift, which has to be a lift fiber-wise also. In particular, if A is separable and C0x nuclear, then every C0x linear CPC map from A to the quotient is liftable. So now we have the lift that we want to average out. Yeah, so we can now average the C0 G0 linear lift that we get by Kasparov and Scandalis' theorem. Yeah, this is the main theorem. So G is a nice groupoid. A, B are G algebras. J is a G-invariant ideal in B. Psi from A to B is a C0 G0 linear CPC map, such that. Yeah, so this says a lot. So note that I do not write phi from A to B mod J. I write psi. This is because I already have a lift. I'll average it out. And what this condition says is that when you go down to the quotient, this becomes equivariant. So you take A from A, go to the fiber of A at the source, apply your map psi, and then the action. So it's, yeah, so this is precisely, so this belongs to JRJ. That means when you go modulo J, this is 0. So these two terms are equal. So that means psi is equivariant to start with. Modulo J. So assume further that A is separable, J is sigma unital, and G is sigma compact. Then there is a sequence of lifts theta n from it's a C0 G0 linear map from A to B. So that the first condition says that when you go modulo J, theta n's and psi coincide. So modulo J psi is my phi, right? The map I started with, phi from A to B mod J. So this condition says that theta n is actually a lift of phi. So we at least obtained a lift. And the second condition says that it's asymptotically equivariant, not exactly equivariant. So when you have a sequence of maps theta, and we'll see what this means in the group case. So this is what we'll be able to get. Yeah, this is the group case, which is much more, I guess. So the second condition here, it says, so this is, if each of these terms were 0, then we would get equivariant lifts. But the theorem says, as n goes to infinity, these terms go to 0. So they're quasi-invariant, asymptotically invariant. There are many ways to say this. And this limit is uniformly on compacts. So yeah, this is the equivariant condition modulo J. So we started with a equivariant map phi from A to B mod J. And this is precisely that condition. And we averaged it out, obtained theta n, a sequence of maps, so that this first condition says that it is indeed a lift of phi. Phi is psi mod J. And for all G, so this is the equivariance condition. And yeah, so this was Forough-Gardella and Thomsen. And this is again us. So this is a special case of our theorem where the algebras are GC0x algebras. J is a G-invariant ideal. Again, psi is a C0x linear map from A to B. So this condition is again modulo J equivariance. assume A is separable, J is sigma-neutral, and G is sigma compact, then you get a sequence of maps theta n, which is C0 is linear, of course, such that the first condition is again, yeah, so the theta n is a lift of phi, and this is the asymptotic invariance of theta n. So yeah, and so we wanted an equivariant lift. Why we are satisfied with this is because this is the one. So what Forough-Gardella and Thomsen, so they proved this theorem because of some applications, and this theorem enables them to prove whatever they were after, and that we generalized in this in the groupoid setting, which is already new when you have G-C0X algebras. It's not even known. Yeah, that's it. Thank you.
Are there any questions? So maybe I'll ask. So this arbitrary trick that you mentioned, it was this Kasparov
Technical theorem.
but it was after you get the C of X and linear, right? Or did it also have to about that?
No. So what Kasparov proved is that you can average an approximate unit, a quasi-central approximate unit, to get a G-invariant approximate unit. And that enables him to prove the technical theorem, which is like the partition affinity.
Yeah.
That you stick together when you define the product, the Kasparov product.
This works for any G, it's not assuming any kind of amenability.
No, it's you need sigma compact.
Sigma.
Yeah. It's for any G.
All right. Something else. We're going to do spot on 5.